Hi everyone, I think we are live now. Welcome to another Memgraph community call. Today I'm joined with Yoan Sallami, a PhD researcher and CEO of SynaLinks. Yoan will demonstrate today how a team can build an advanced AI systems using open graph tools and how SynaLinks is pushing the boundaries of a graph-powered neurosymbolic AI. I hope I said everything right. And we're also going to have a demo after the presentation, so stay tuned for that as well. Before we begin, just a reminder that we have a chat here, so feel free to chat with each other or ask any questions you have during the presentation. And we'll have a Q&A session at the end where Yoan can answer any questions that you have. And we also have some polls in the polls tab, so feel free to cast your vote there as well. And yeah, that's it from me. I'll now sit back and enjoy the presentation along with you.
Okay, so hello everyone. Thank you, Matea, for introducing me. Today I'm gonna talk about a very recent software that we developed at SynaLinks, and that software is inspired by Keras. I don't know if some of you are familiar with it, but it's deep learning frameworks that was developed 10 years ago. So it was very groundbreaking at the time because of its user friendliness. And today, the most LM frameworks are very opinionated, and they have a structure that makes them difficult to use. So our idea for this software was to take inspiration from decades of research on making this kind of architecture usable for people. And so we created SynaLinks. So SynaLinks is a fork. Actually, we didn't start from scratch. And it's a Keras fork, and it's more specifically been made for neurosymbolic applications. So for us, like neurosymbolic applications are focused on three things. First, workflows. That means that you have a system that is structured, what we call the program, where you describe a directed acyclic graph of modules, and each module performs a computation. And the second aspect is knowledge graphs, as we are going to see what it means in this context of LLM applications. And the third aspect is optimization. So we wanted to emphasize these three aspects that are required when you are making business applications, because most of the time what engineers might be doing when they want to integrate LM, a large language model, is they spend a lot of time making the system robust. Like, we now have more or less, we have reached a certain capability with large language models, but there is still many challenges around robustness and usability. So I'm going to start by showing you my screen, so we can I can present you the frameworks and how it works. Okay. So really what is interesting in SynaLinks is that, so wait, so I can show the instruction. Okay. So what is interesting in SynaLinks is that instead of writing prompts every time, the only thing that you need to do is to describe your data models. So the data models is in this case a pydantic model, and we use it to describe the fields of the inputs of the module and the outputs. So after defining the input data model and the output data model, we can generate a pipeline by just chaining modules with each others. And this way of chaining the modules is actually inherited from Keras. This style of programming was actually introduced by Keras a decade ago. And based on that, we are able to create a pipeline. So this pipeline, for instance, is a chain of thought. So chain of thought is a classic techniques that is used in language model applications. And we are able to create these kind of things very quickly and very easily. So how do we deal with knowledge graph? So in order to create a knowledge graph, what we emphasize in SynaLinks is that a knowledge graph is just a data model. It's a way to model data with nodes and edges. And SynaLinks by default use constrained decoding. So the constrained decoding, it's a technique that nowadays is available in most language model providers, and it's a technique that's guarantee that the response from the LLM is going to satisfy some JSON schema. And in SynaLinks, what we create when we generate a pipeline, we actually specify not only the data but also the schema along the whole pipeline. So if we look at the display of the program that I just showed you, you're gonna have like the input schema with the query of the user and the data model, the output data model. And this output data model and this input data model have been defined using pydantic structures. So that's it is created automatically. So now, let's say we want to create a knowledge graph. So let's say we want to create a knowledge graph. So in SynaLinks, a knowledge graph, as I said, is actually data models. And we can specify the data models by creating a data structures that's gonna have a label for entities and also for relations. So we can have a relation for labels and the relation for entities. What is different from other frameworks in SynaLinks is that the knowledge graph is not opinionated. What I mean by that is that the only requirement for the data structure is the label. The label is then used for creating the node with a label in the graph database, and all the other fields are optional. You can have, for example, heterogeneous knowledge graph with SynaLinks and extract them as you want. So that's really important because we wanted for this framework to be adaptable to any business use case. For instance, you might want so this is more toy examples, but in a business use case, you may want to have different fields for certain entities, and other entities maybe have just a name and a description, and other may have a completely different set of attributes. So we wanted to be able to extract information from documents or from anything, and not be opinionated in the way that we describe the entities. So this is how we create the entities, and now the relation. The relation is a bit more complicated in the sense that in SynaLinks we have to describe, for example, the subject. For example, we created a relation that is called is city of, and this relation connects a city to a country, okay? And it has a label. The label is important. So in a relation, you have to define the subject, the object, and the label. And you can optionally add other description, like a description, or other field like a description, a name, or anything, any metadata that you want. And the system will be able to extract those metadata based on the schema provided. Now, how we extract relations that might connect different types of entities. So in that case, we can create an union, and by doing so, we can specify, for example, in the is located in. So the subject is a place, and it might connect to a city or country. Okay, and this is the way we ensure that the relations can connect to multiple types of entities. What is key to understand also in SynaLinks is that the schema is enforced by the constraint decoding. So we can ensure that the schema is respected. It doesn't mean that the extraction is going to be perfect, because there is different things to consider when you want to extract a knowledge graph for documents, for example. There is the first aspect is the schema respected? So is the syntax of the knowledge graph respected? And then there is the content. There is these aspects are different, and in SynaLinks we can enforce that the syntax is respected, that the schema is respected, but in order to have also the content, the perfect content, that's when it gets a bit trickier. So we have in SynaLinks different. Yes. Yes, actually everything is pydantic. Under the hood, all data models, all relations, all entities, everything is pydantic. We use pydantic everything and for everything and everywhere. That's how we serialize and create the schema based on the data that is provided. So yes, that's everything is pydantic. Okay, so now how we are going to extract the knowledge graph. I show you at the beginning a simple program where we asked the LLM to answer with the thinking, and we used the generator, and that generator was add a data model that was specifying the thinking field and the answer field. And we can do almost the same thing, but instead of creating, for example, let's say you want to extract a knowledge graph. You have a very powerful large language model, and you want to extract everything in one go. So you create a pydantic class, And that class gonna have like a list of entities, and each of entities is a city, a country, a place, or an event. And the relations are the relation that you have in your graph, basically. And so it's a list of union. So we're gonna let the LLM choose in that list which relation is which relation he wants to extract based on the inputs data that is fed into the large language model. And this is this is actually a Pydantic class, and we are going to use a generator. So that generator, we ask them to have to extract this data structure. So we give it as data model the class that we just declared, and we give it a language model. And then we chain the inputs. And that way we are going to extract the knowledge graph. Now, we want to embed the knowledge graph. Let's say you want to create a retrieval augmented generation pipeline, and you want to embed the entities in that knowledge graph. So to do so, we can use another module, and this module is called embedding. You define the embedding model that you're going to use, and you define a mask. The in mask defines the fields that we are going to keep in order to compute the embedding. So in that case, we are computing the embedding based on the field name. So for each entity, we're going to extract the name from all the fields that have this entity, and we are going to feed that into an embedding model, and the embedding model is going to give us a vector, and that vector is going to be attached to that data structure. And then we can then update the knowledge graph, and we can do it by just giving the knowledge graph to that module, the knowledge base to that module, and we chain the module with each other. So it's a very declarative way to work, where you just have to define your pipeline in a very easy to use declarative style. So here you define your input, your program from inputs and outputs. So that's, again, if you know Keras, you're gonna see a lot of similarities, because actually it's almost the same code base. And you can plot your program. So you can plot your program, and that program is gonna be plotted. You're gonna generate a small figure like that, and that figure gonna tells you like there's an input module, a generator, an embedding module, and then you update the knowledge base. I'm gonna show the demo at the end. First, I want to dive into the docs and show you everything without the problem that can occur while doing a live demo. So then imagine you are in a company. There is a good chance that the knowledge graph that you want to extract is heterogeneous. What I mean by that is, I mean that each node or each relations won't be the same difficulty for the language model to extract the data. For example, if you have a relation with a lot of fields, then it's going to be hard for the LLM to extract that data. If you just have a name and a description, that's going to be okay-ish. You can even use local large language model. That might not be enough, but that's okay. If you have, for example, let's say you have one of the nodes is a report. Let's say you are a security company, and you want to extract a knowledge graph from incident report. You're going to have some nodes that are, for example, the person in the company. So that might have just the name, an email address, and things like that. A nodes that model a computer, where you are going to extract the name of the host, the IP, and stuff like that. And then there is some nodes that you want to, for example, create a node. Yeah. Okay. I'm gonna go to that just in a moment. So then you want to extract so a node that's a node of the incident report, and that node is going to have a lot of fields. And in that case, what you want to do is to have a pipeline that is really modular, because you cannot you're going to have to deal with the nodes that have different difficulties for the extraction, and you want your pipeline to be really really configurable. So in SynaLinks, what we can do, for example, is we can do a two-stage extraction. In that case, in this example, we are going to extract the entities first, and then the relation first, and then the relation in second, and we are going to aggregate all that into a knowledge graph. So we have the input, the first generator that's going to extract the entities, and then we are going to extract. We give, along with the inputs, the entities that are extracted, and then we are going to extract the relations. We combine the relation and the entities, and we embed and update the knowledge graph. Okay, so this is going to create you a different knowledge graph that might be better depending of your use case. So in the multi-stage extraction, for example, this is where we get the maximum controllability of the system. We can ensure that, for example, we can create a Pydantic class that only extract the cities, one that only extract the countries, the places, and so on. And we can create a very complex pipeline where we chain the generator in a parallel fashion, and so the program that you're going to end up is very much more modular and much more accurate, because you are actually splitting the task of, instead of asking an LLM to generate a whole knowledge graph in one go, you're going to ask the LLM to just generate part of the graph, and that the part of the graph that you are going to generate is configurable, and you can do as you want for that. And you can, of course, you can combine all those relation and entities very easily by using a logical operator. So the logical operator, they are very much like operator that you can have in a programming language. In a programming language, you have operator that are going to represent like and, or, and you can do that. The or, for example, is going to ignore, if one of the generator didn't work, is going to ignore it and generate the entities, the entities and the relation. So we can end up with very much complex knowledge graph. The last thing that I want to emphasize is that because in the relation we have the entities, we can actually just extract the relations, and we can end up, by just extracting the relation, we can end up with a simpler program, and we can guarantee that the knowledge graph extracted don't have orphan nodes. That's often important in a knowledge graph application, because you want your nodes to be connected in order to work on that and to extract relevant facts or detect communities and so on, this kind of thing. Okay, so I'm gonna start first I want to Have you tested this with entities which are defined across multiple unstructured inputs, different page of a PDF file? Okay. So about multiple documents and the inputs of file. Actually, yes, that's something I'm going to show you. The challenge in that case is that you have to deal with the deduplication of entities in your graph in order to connect the relation from different pages and different documents into one unified graph. And in SynaLinks, we do that automatically by using the vector index of the graph database. So when we update a node in the graph database, we, instead of having a Cypher query that is just like create or merge the node, we have actually a query that is a bit more complex that is going to perform a similarity search. And then if there is no similar nodes, we create the node, and otherwise we update. So that's that way we can have a deduplication, and by using the hierarchical small word k-neighbor of the vector database, we can actually like do the duplication with a very good speed, instead of relying on the Hungarian algorithms to duplicate the nodes. So we do that automatically, but the computation, the heavy computation, is actually done by the graph database, not done by the framework. We just query it in a smart way. Yes. So the generator, the data model is converted into Cypher in order to update the graph database, obviously, yes. So yeah, yes. So you can have an already existing database and works with it, but you are going to need to define the schema that you are already using. So that means you're going to have to, in order for the system to work perfectly, we require a schema to be working. That we might in the future add some methods to extract a schema from an already existing graph. But right now, if you want to connect to an existing graph database, that has an existing schema, you're going to have to define your schema in Pydantic. But we might, in the future, able to retrieve the schema and convert it automatically into a Pydantic structure for later work with it, to work with it. About the simplification of the graph construction, I think I already tried to use an agent like Cursor or stuff like that to create the schema. So you can use that. That's going to help you to simplify the creation. And because the data structures is actually Pydantic style, the LLM are good enough to do it. But the problem in knowledge graph techniques usually is that the schema needs to be designed by people that knows the problem they are trying to solve. And it's very difficult for an LLM to grasp that. So obviously you can have an assistant that helps you writing the schema, but at the end, writing the schema is not the most difficult part. The most difficult part is actually modeling. So how do you think about solving your problem? What's the kind of queries that you're gonna use? What's the purpose, basically what's the purpose of the knowledge graph, and how you're gonna use that technology to solve your problem. That's why we didn't want to have an opinionated way of describing the nodes and the age. So we try to reduce that to the minimum in order to have something that works, that can connect to all the ages, retrieve the right label for the node and stuff like that. But we wanted to keep it at minimum because basically we use SynaLinks, we use it for our business applications and when we work with clients. So each client have different needs, and it's very not efficient to have a very opinionated way to model your node and relations, because you might end up with business use cases that invalidate what you have been done. So there is ways to simplify the construction of the graph, but usually that's might be a bad idea, because you need someone that is familiar with knowledge graphs. I think that knowledge graphs are one of the easiest to grasp techniques in artificial intelligence. So it might be good for you to just spend a bit of time on it, because that's going to be life-saving for the future if you want to make a business out of knowledge graphs, for example. So I'm going to start the demo. So let me change the sharing of the screen so I can show you the code and everything. Okay. 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 So here is the pipeline to extract the relation only for your knowledge graph. I'm going to use this one. It's a bit more complex. So it's basically the same example than before. The only difference is going to be like I'm connecting to Memgraph instead of Neo4j. And basically that's the more or less the same extraction pipeline. So if you look at here is the pipeline, how it looks like. So we have one generator per type of relations, and we combine each of them using the OR, and then we factorize. The factorization is actually we group when we do or an AND, if there is multiple fields with the same name, we add a numerical suffix to it, and that numerical suffix we use that when we factorize. We actually group all the keys that have the same base name and might have a different numerical suffix, and we all group them. So that's basically allow us to aggregate the data in a very simple way, and then we can embed them and update the knowledge. So in that example, I had a question previously about extracting multiple pages of multiple documents and so on. I can show you the data set that I use in this example. So it's a toy example. It's not really complicated, but each page and each document, we actually process different pages and different documents, and the node is going to be connected by the deduplication that's going to happen on the graph database. If you want to, like the cipher query is a bit like, it's not a very big cipher query, but it's a bit complex than what you might be used to in other frameworks, because we, instead of doing the deduplication using the Hungarian algorithm, for people that don't know the Hungarian algorithm, it's matching algorithms with linear complexity, and it's used in multi-object tracking in computer vision, and it's also used in deduplicating entities in knowledge graphs. Oh, like always, let me start again. I had just a small problem. The Docker container, the Memgraph Docker container, just disconnected previously. I forgot to launch it. Let me do that. Okay. Okay. Launch again. Is it launched? Yes. Okay. Should be good. Again. Takes a bit of time to launch because I use a local LLM, so the model needs to be loaded into the graphic card before. Okay, that's started. Okay, everything good. Let me change the screen so I can show you the Memgraph Lab. Okay. Okay. So here is the graph. It's going to extract. So this is like the beginning of the extraction. And as it processes documents, we are going to see the graph growing. And each document is independent. And then the nodes are merged, are deduplicated using the index of the graph database. So actually, that's very efficient for large graph because we can ensure that the duplication is done in a logarithmic complexity. We just had another document, and so on. If you have any question, like I can answer them while we wait for the extraction to happen. There is to answer the Raoul Vitli, sorry if I pronounce it wrong. In SynaLinks, the way I usually write the schema, I constrain different types of entities and different types of relations. But actually, you could create a knowledge graph without any constraint on the schema. But if you do so, there is a good chance that your LLM gonna end up with a very bad extraction pipeline, with a very bad extraction. So it's possible, and I can show you how. That's very, if you're very familiar with constrained decoding and using Pydantic for large language model applications, you already know the answer. So let's say, okay, I can show you that, just a moment. Okay. Let's say we want, like, if you just give an if you just create like a class, an entity, and you create a label that's going to be a string instead of a literal, like something like that, the name of the entity. Then basically you are not giving any constraint on the label that the entity is going to be created, and you can do the same for relations. But beware that it's not really something that should be done. It's possible, but your language your knowledge graph might end up being a big structured garbage if you do that. But that's possible. If you use a very powerful language model, or one that have been fine-tuned for your specific use case, then that might make sense. Okay, we can go back to the Memgraph Lab. So the document processing is finished. We can refresh the query, the graph. And that's the resulting graph. Because we specifically extracted only relation and not entities, we can ensure that there is no orphan node, which is very convenient, because that's a recurring problem with LLM extraction. So do you have any more questions? It's so almost every problem can be modeled as a graph, as a knowledge graph, but it doesn't make always sense it depends on what you want to do with it. Knowledge graphs are really good for applications that deal with relational data. And you can use, for example, a knowledge graph to just like do a regular RAG by storing chunks, documents, like doing basically very much like Microsoft's Graph RAG. So you can there is no limits in the way you can model knowledge graph. The only limit you have is that what you can model is triplets. So it's subject, relation, object. And in graph databases, you don't have reasoning on relations like you could have with ontologies, with RDF and things like that. So that's the only limit. But what is better in graph databases is that you can attach like metadata in the relations and reason on the data with specific data for your relation, entities, and so on. There is more freedom in the way you can model your problem in knowledge, in property graphs. But there is more freedom, there is less constraints, and of course, then the knowledge graph that you want to build is really domain specific and problem specific. So I took the example of a security company previously, and that's something like, for example, you have to create a knowledge graph specific for that problem for that company. You cannot have, there is no one-fit-all solution with this technology. It's always a trade-off, and you have to be aware that some problems are better solved with knowledge graphs. Others can be solved without it, but often like dealing with knowledge graph is in general a better way to deal with data. It's not necessary all the time, but it's often best to have this view of connected data and how you can generate insights based on that data. That could be the connection. That could be, for example, let's say you are a biology company. You model the molecule of interest, and you model each effect of each molecule, the composition of your products, and you want to be able to link the effect with the composition or with the molecules, etc. And that's the kind of application where knowledge graphs really shines. And there is no limit on that. Also something that I want to emphasize is I see this, like many people that start in knowledge graphs, they want to start extracting with a LLM. As a professional, I won't do that. You always want to extract your knowledge graph specifically if you already have a structured data. Let's say you have company data and stuff like that. You want to use an LLM to extract the data only if you can't do it with a regular script and so on. And in SynaLinks, you can also create a module. I didn't explain it because that's beyond like the first tutorials that I share usually, but you can create a module that's gonna have like just Python code and extract the data from a structured document in a more deterministic way, and that's the first thing that you should do if you deal with knowledge graph, is like creating a script to extract your knowledge graph, extract your data, and work from that. If you can't do it because let's say you have unstructured documents, then using a large language model for that makes sense. But if you are working, for example, in finance, healthcare, anything that is sensitive, your knowledge graph should be like the cleanliness of your knowledge graph should be your priority number one. Like you cannot let LLM do that. You can use it to retrieve the information, but to extract the knowledge, that should not be done like this way. This is really for unstructured data where you can't like use regular or old-fashioned ways to extract knowledge graphs. And in that case, that makes a lot of sense to use that. But otherwise, just don't do that, because you're going to end up with a noisy knowledge graphs. And except if you use the Microsoft Graph Rag implementation, which is basically like, it's not entirely a knowledge graph. It's a graph, but you detect the communities, and then you create summaries of those communities. But at the end, it's a vector rag. So you carry a vector, and you have just a string, and you carry a vector, and you get an answer that might be a chunk or a summary. And that way, these techniques are less sensitive to noise, but otherwise, knowledge graphs in all the fields that have been using them traditionally, like fraud detection, finance, healthcare, legal tech, and all that, you want to have a clean knowledge graph. That's really important, and you cannot like do everything with the LLM. Like, and it's not like a big deal. Someone with a bit of experience in knowledge graph can end up with a good first schema to work with, like in few days. It's not something that should be like it's not very difficult, but you have to bring human expertise in that. Even if it's just to create the schema, and if you then use a LLM to extract the information, you want to have someone that define what's going to be important in your schema and your knowledge graph. I previously talked about using Cursor to create a schema and stuff like that. It's true that it can be useful, but if you don't know how to model a knowledge graph, you won't be able to detect any inaccuracies in the schema made by the AI assistant, and you might end up with a garbage, like structured garbage, basically. Like you cannot exploit your knowledge graph. Something that I see a lot in our clients is that they jump straight into extracting knowledge with the LLM, even if they already have structured data that they could extract with a regular script. And that is a big mistake that should be avoided if you are a professional in this field. I think I'm done. So.
Yeah, thank you. You answered a lot of the questions from the audience. We do have one more question in the Q&A tab. So the question is, you currently relate relationships with the same name by appending the numbers. What if the relationships are not coherent? So what if they're ambiguous? So this happens in involving knowledge domains, especially when different disciplines are involved.
So there is different things. So ambiguity for us or for the LLM, it's different. The question is different to answer that. Something that is important for LLM is that you have to keep in mind that they reason on tokens. Let's say you have two relations and they almost the same, like, and they have tokens in common. So that's a mistake that you can make, because if you reason just as a human, you say, for example, contains, not contains, these kind of things. This should be avoided if you use an LLM to extract the knowledge graph, because if there is a lot of token in commons, that means the LLM is going to have ambiguity in the embedding space. So if the embedding space is like a 3D, you can visualize it as a three-dimensional space, and you're going to have like words that are similar that have tokens in common is going to be like more close to each other, and so there is higher probability that the LLM is going to end up doing mistakes. So if you can use words that are very different from each other, and they might end up having the same meanings, but they just different in the way you write it, that can help the LLM to extract the knowledge. If your schema is not, if you made a schema that is not coherent, let's say you are a complete beginner, you use cursor to end up with a schema, you feed them like our first tutorial on knowledge graph. It works. You can feed it the tutorial, you give it to cursor or to Claude, you describe a bit your problem, and you're gonna end up with a schema. There is no guarantee that this schema is gonna be correct. And if you don't have the capability to spot it, to spot the mistakes, you're gonna lose a lot of time. And possibly the money if you use it as a basis to extract your knowledge graph. For a professional, it makes sense because it might speed up the writing, how to write the schema, but they are going to spot the mistakes. But otherwise, if the schema is not coherent and basically your knowledge graph is not coherent, well, that's on you. The knowledge graph usually this is not something that is specific for knowledge graph. In symbolic AI, which is the field of AI that was really trendy before deep neural networks, most of the techniques don't deal well with noisy data. It can be like, for example, if you have a symbolic planner, it don't deal well with noisy data. You need to have clean graph, clean ontologies, and there is techniques to create those clean data structures. But obviously, that's a bit more difficult for a beginner to do, because you cannot use a probabilistic system to create the knowledge graph or the data structure. I forgot to mention that my background is actually in robotics. So in robotics, we use a lot of symbolic AI for long-term planning, for reasoning on space, time, and things like that. Almost everything is a graph in robotics, from the joints in the robot to the scene where you have your object and stuff like that. And it's important to have a good data. Like, there is a lot of something that I want to emphasize, like in computer vision, for example, the computer vision revolution happened a few years ago, and it's not big, like, now we have better detector, better things to detect objects in the scene, people, and stuff like that. But we still use Kalman filters. Like, we still use techniques to robustify the output of deep learning. And most of the work of engineers in AI are about cleaning the data, making the system robust, and stuff like that. So that's something that should be done by professionals.
Yeah. Thank you for all of your answers. I think you now answered all the questions from the audience. And thank you, Greg, for the great presentation. It was a really interesting topic to hear. And I hope everyone enjoyed it as much as I did. I already mentioned in the chat, but the recording will be available on Memgraph's on-demand page. I've posted a link in the chat so anybody can rewatch if they missed anything. But yeah, thank you again, and I hope everyone has a great rest of the day, and I'll see you on our next community call.
Thank you very much, Matea. And thank you everyone for being present. Bye-bye.
Bye, everyone.